Greetings and thank you for watching this video. My name is Daniel Pradel. I'm a principal engineer at Group Delta Consultants and a professor at UCLA. This is the outline of my presentation, a small preamble, and then we'll be discussing items related to earthquake risks. I'm a civil engineer by training, and if you go to the yellow pages, on the boring it says "See Civil Engineers." I hope this would not be what you will feel at the end of my presentation. As of lately, I am asked a lot about what is soil liquefaction, and as a preamble I thought I'll show you this building sitting on loose saturated sands. When the engine starts and causes vibration, the heavy building sinks into the liquefied sand and settles considerably. I saw a lot of evidence of liquefaction in the town of Fusa, just north of Tokyo, Japan, after the magnitude 9 Tohoku earthquake in 2011. These are buildings in the main street of Fusa that have settled significantly, and we're going to concentrate on the building on the right. This is the front of the building. You can see that it has settled towards the left. Why towards the left? Because it's heavier on the left due to the presence of a tower. Let's look at the tower. As you can see, it has very little structural damage. However, it has settled significantly. Look at the door. This is a close-up, and it's obvious that this portion of the building has settled in excess of 2 feet. This is another view of the tower. If you look at the window at the base, it almost appears to be a crawl space entrance. Again, very little structural damage in this picture. This is a single-family residence located nearby, and once again we see very little structural damage. However, if you look at the balcony is severely distorted. It almost appears that the balcony has gone up on the left side, or that the building has gone down. If we look at the entrance of the building, it's very clear that the building has gone down by about 1.5 feet. Let me now address earthquake risk. In particularly, how often earthquakes occur, where do they occur, and how are different areas affected. In California, everybody is concerned about what they call the big one. And the big one is associated with a 7.7 to about 7.9 earthquake on the San Andreas Fault. Typically, these earthquakes occur every 150 years over a given area. It usually starts slipping in the south and moving north. If we look at damaging but lesser magnitude earthquakes like the 6.7 Northridge earthquake, in cities like Los Angeles and San Francisco, we have about a 2/3 probability of experiencing one over a 30-year period. Some probabilities that you can find in the literature will say that, for example, in Southern California, we have a 97% probability of experiencing a 6.7 earthquake. However, it's not likely that a 6.7 earthquake would affect the entire Southern California. If we look at the area of damage from the Northridge earthquake in this map here, we see that it was relatively confined, especially compared to the magnitude 6 1895 earthquake that affected the area of New Madrid, Missouri, and nearby towns and states. Why is that? Because the bedrock in Southern California, or in California in general, tends to be relatively soft, especially compared to the hard bedrock that you can find in the East Coast. And soft rock dissipates a lot of energy as the earthquake travels through it. 10 years ago, I used to say that we can expect a damaging earthquake in Los Angeles typically every 10 years. In the 70s, we had San Fernando. In the 80s, we had Whittier Narrows. In the 90s, we had Northridge. However, the last decade, we were lucky. If we look at the number of damaging earthquakes since 1960, we've had a little bit less than 40 in the magnitude 5 range, a little bit less than 40 also in the magnitude 6 range, less than 20 in the magnitude 7 range, and very few in that were greater than 8. The probability of death from an earthquake is very small. It's less than airplane, bicycle, or even lightning. And if we look at the large earthquakes that have occurred in the US, we see that the total number of deaths has been relatively modest, especially compared to things or to disasters like Hurricane Katrina. The ones that have had the larger number of deaths had either tsunami or fire associated with them. Where do earthquakes occur? Well, they can occur on faults that are visible, such as the San Andreas Fault. The strike-slip faults are very clear, geologically speaking. You can actually see the San Andreas from an airplane when you fly towards the East Coast. Blind thrust faults are more difficult to identify, and they're the ones that have caused the large damaging earthquakes in Los Angeles in the last 4 decades. In areas that have bedrocks, the major faults are known and have been mapped. There are some blank areas in this map, for example the Central Valley, and the reason is that the bedrock is covered by hundreds of feet of alluvium, and therefore the exact location of the fault cannot be explored or mapped by a geologist or engineer. Now let's talk about how different areas are affected, and I'd like to introduce the concept of magnitude and intensity first. Magnitude quantifies the energy released by an earthquake. For example, we say that Northridge had a magnitude 6.7. The intensity describes the level of shaking or damage at a specific location. So, for example, the intensity at Santa Monica was different than at Beverly Hills or Studio City during the Northridge earthquake. Because the magnitude scale is related to energy, we can relate it to things like explosives, lightning, and other energetic events. A magnitude 6 would be roughly the energy of an atomic bomb. And typically, when you have a magnitude 5.0 or less, there is no damage. So how can we use this scale to quantify earthquakes like Northridge in '94 or Tohoku in 2011? Northridge earthquake, which had a magnitude of 6.7, had the energy of approximately 7 Hiroshima atomic bombs. Because the magnitude scale is logarithmic, when you move from a magnitude 6 to 7, you increase the energy by 32 times. When you go from 6 to 8, you increase the energy by 32 times 32, so almost 1,000. And that means that the energy from the 9.0 Tohoku earthquake was about 2,900 Northridge earthquakes, or about 20,000 atomic bombs. The intensity scale describes the effect of an earthquake at a particular location. An intensity of 1 to 5 involves earthquakes that are felt but that do not have damage. And damage starts at 6 and above. Historically, there are many states that have experienced earthquakes that are more intense than California. In terms of magnitude, we had the magnitude 9.0 Great Alaskan Earthquake of 1964. In terms of intensity, if we look at New Madrid, we had a very large area that actually experienced very high intensities. Because the bedrock in the East Coast is a lot harder than the bedrock in California, the area of intense damage from the New Madrid earthquake was much more significant. If you don't know where New Madrid is, this map will help you. It's basically very close to where Kentucky, Tennessee, and Missouri meet. This is an intensity map for the 1812 magnitude 6.5 New Madrid aftershock, and you can see that the area that had magnitude 6 and above involved numerous states. For many years now, we have been using the California Seismic Network. If you want to access it, the best way is to write shake maps in Google and go directly to the web page. And usually you'll have information about a particular earthquake within 10 minutes of that earthquake occurring. The shake maps have gone from being limited to California to now being used for earthquakes worldwide. This is a recent shake map for an earthquake that occurred near Big Bear, and you will see that the shake map will give you areas of potential damage that will be color coded. In this area, in this particular earthquake, basically the damage potential was none. Let's now talk about site effects, or what I like to call the jello effect. If you have a piece of gel on the table and you shake the table, the top of the jello may move a lot more than the table itself. It will amplify the shaking. A clear example of site effect and ground motion amplification occurred during the 1985 Mexico City earthquake. The earthquake was actually closer to Acapulco than to Mexico City, and was located at the epicenter was located 220 miles away. However, in the South Lake deposit of Mexico City, the ground motions really intensified. These are two accelerometers. One is in the foothills of Mexico City, UNAM, and the other ones are in the lake deposits, and you can see how much the accelerations were amplified by the soft lake deposits. Amplification also occurred near Oakland during the 1989 Loma Prieta earthquake. Here in bedrock, we see relatively modest ground motions. Here in the soft mud deposits, we had really large accelerations, and the area where the Nimitz Freeway collapse was in the soft mud deposits. This is a picture of the collapsed Nimitz Freeway. Let's talk a little bit about coastal areas. I went to the tsunami affected areas during my visit to Japan weeks after the 2011 Tohoku earthquakes, and it's very hard to tell you how you feel in areas that were occupied by cities and that were devastated by the tsunami. In terms of the mechanism, the island of Japan was pushed inwards at a rate near 4 inches per year, and the island of Japan literally bounced back, creating a large wave in the middle of the Pacific, which created waves going towards Japan and towards Hawaii. This is a simulation of the wave. There was the first wave that hit the coastal, and then afterwards there were secondary and tertiary waves that came back and hit the coast again. The first wave overwhelmed many of the protections that they had along the coast, but if you've seen the videos or, like me, spoke with the people living there, they had ample warning and very few people were actually on the streets when the first wave came in. The problem was the secondary and tertiary waves. The people that we spoke to told us that it was the people who had to check their homes, wanted to check on their family and pets, that left after the first wave. Those are the people that did not come back. As engineers, we usually look at the effects of the tsunami in terms of run-up height. There was the maximum run-up height or elevation that was measured was in the order of 120 feet. But there was a large area of the coast where the waves reach an elevation of 30 to 60 feet above sea level. If you don't believe me, you can look at this picture where we see debris sitting on top of buildings that floated during the tsunami and came to rest on top of buildings. This is a boat. And many of the cities in Japan had some level of protection. These are some tsunami walls south of Sendai. This is actually a street that actually has a gate. And when we looked at many of the tsunami protection levees and walls, many were largely destroyed after the first wave of the tsunami. The tsunami was predictable and was the reoccurrence of something that had actually occurred before. People in my specialty knew that there were tsunami deposits. That means sand that was brought up by tsunami up to elevations of about 125 feet. And after the tsunami water left, these deposits were left on the ground. In Japan, these deposits were very well preserved because after the 869 tsunami, which is available in the history of Japan, the Nihon Shoki, was a volcanic eruption from the Towada-A that left a layer of ash covering these tsunami deposits and preserving them. The Japanese, in the report to the International Society of Soil Mechanics and Geotechnical Engineering, basically acknowledged that the tsunami was similar to the one of 869. And one of the lessons that I learned from my trip to Japan is really we cannot ignore history. One of the reasons why engineers like myself care so much about the Tohoku earthquake is because if we look at the fault that caused the Tohoku earthquake, we have an almost mirror image in North America. This is called the Cascadia Subduction Zone, which is next to Northern California, Oregon, Washington, and all the way to Canada, that we know produces typically magnitude 9 earthquakes every 500 years or so. We can look at the two last magnitude 9 earthquakes and plot them in terms of length. The 2004 Great Sumatran earthquake is shown here in black. In blue, we have the length of the 2011 magnitude earthquake. And it's very clear that when we have the Cascadia subduction zone earthquake, we'll have more than one state, if not internationally, effects from these earthquakes. Soil liquefaction, last topic. The earthquake that brought soil liquefaction to attention in North America was the 1964 Great Alaskan Earthquake. This is a neighborhood in which ground liquefaction took place, and if you look at an aerial view, the area where the liquefaction took place is very clear to see because you see hardly any snow on the ground. This is another nearby neighborhood. This is a building that has been severely affected, and this is a neighborhood where that building was located. Once again, you can tell very well the zone that was affected by liquefaction. You can also see in this picture some of the homes that were outside of the liquefaction affected zone. In Japan, that same year, there was another major earthquake that also caused widespread liquefaction. It was the Niigata earthquake. And here are some images of buildings that were severely rotated. The phenomena is similar to the one that I showed you at the beginning on that small video where the building sinks into the ground. Some of the buildings were more affected than others, and it had to do with the builders trying to save some money and replacing concrete foundations with boulders instead of concrete. We had widespread liquefaction in 1989 during the Loma Prieta earthquake, particularly in the Marina district, with many buildings collapsing or being displaced significantly. Well, as buildings go down during liquefaction, if you have something that can float, like here these manholes in Japan, they will do the opposite. They will come up to the surface. And in Japan, I saw entire cities or neighborhoods where, due to liquefaction, the utilities became disconnected from the buildings. Either the building sunk, the utility lines floated to the surface, or when you had buildings like this one that was built on piles, they became completely disconnected from sewer and water supplies. This has occurred during numerous earthquakes before. We saw it in, for example, Turkey. We also saw it in Mexico City and many other locations. Different buildings are affected differently. And there are some structures that are particularly vulnerable to damage. The ones that are the most prone to damage historically in the US have been the unreinforced masonry buildings. And very often we want to keep historical buildings, but these historical buildings can become very prone to damage. We've seen it after the 1987 Whittier earthquake. We've seen it after the Coalinga earthquake. These buildings tend to be very, very vulnerable. Another type of building that is very vulnerable is what we call buildings having soft stories. These are buildings where there's a lot of openings along the base, and therefore essentially no wall to carry the lateral loads from the earthquake. A very good example is this building here in 1989 during the Loma Prieta earthquake. The lack of wall at the level where the garage is allowed it to essentially deform, in this case here, towards the left. Please note that there was very little structural damage in the areas where there were large walls. That means the second, third, and fourth story of the building. We've seen this type of damage again and again during earthquakes. Here we see it at the Olive View Hospital during the San Fernando earthquake. At this level over here, where it doesn't have enough lateral capacity. And of course in Northridge earthquake, a large number of people died in this apartment complex known as the Northridge Meadows. The damage that I saw in Japan after 2011 was considerable in pre-1970s building that were not seismically retrofitted. We have this old building here that literally pancaked or became flat on the ground. This is a building that actually had a crawl space, and the crawl space was not reinforced with plywood or anything else. Here we have a small office building with, at the lower level of the building, no wall to actually carry the lateral load, and that's why we see this side wall that has been completely become detached from the building. What I was very happily surprised was the virtually lack of damage in modern construction. Buildings in Japan that had been either built after 1995, after the Kobe earthquake, or that had been retrofitted were basically undamaged from the magnitude 9 Tohoku earthquake. Next, let me address structural response. Distance from an earthquake not only affects its intensity, but also the frequency content. And the frequency is very important to the structural response of buildings. If you're close to the epicenter of the earthquake, you expect to have, of course, larger motions. And for example, in the 1994 Northridge earthquake, we had the parking garage on campus that collapsed. But when buildings are very close to the natural frequency of the earthquake, what you can have is that you can have the building become resonant. And if it becomes resonant, then you can have the upper stories, for example in this case here, that collapse and become pancaked. Here we have two buildings, an old building in the front that lost maybe some stucco in the front, but they behave very well. That was not at the natural frequency of the earthquake, and the building in the back that was very badly damaged and pancaked because it was close to the natural frequency of the earthquake. Hillside Properties, we had numerous structures that collapsed in Los Angeles because they were built on stilts. These are very vulnerable structures. We also had slope failures, landslides that occurred. In Japan, during Tohoku, they had over 3,000 landslides. Many of the slope failures luckily occurred in areas where buildings were not located. But that is not always the case, as we see here in 1964 during the Anchorage earthquake. In addition to that, buildings built on slopes, on hillsides, are often at the transition between compacted fill and native material. And what we tend to have is settlement that occurs in the fill, and also separations and lateral movement that occurs where the home is located in the back. You see it here in this picture. Please note the large amount of distortion on the windows in this house. In this slide, the slope is located to the left, and the patio slab in the middle has moved towards the left. A foot wide separation is now present between the patio slab and the concrete slab of the home, and this wall over here has actually become separated from the home slab itself. Unfortunately, a lot of hillside homes were similarly affected during the Northridge earthquake. With this, I wanted to thank you for your attention. I hope you've enjoyed this presentation. On behalf of everyone at Group Delta, I want to thank you very much for your attention. Goodbye.